So we're talking about spectral types of stars, and one of the things here that we look at are the spectral lines. Well, Walter Adams, American astronomer, discovered something really interesting about these spectral lines, and that is that you could have two stars that are the same spectral type. So that means they're the same temperature, but one of them might have very thin spectral lines, one might have fat spectral lines. Now, he wasn't exactly sure at the time why that was the case, but now we know that what's happening is as the atoms, that you have stars, and the size of the star basically has little to do with the mass in the star. You can have a really huge star and a really small star that have the same mass. The small star is more compact. So the molecule atoms bump into each other in here more than they do in the bigger star. When the atoms bump into each other, then the spectral lines actually get a little bit fatter. And so what happens is you get fat spectral lines in the small stars. So that means the fat spectral lines correspond to a small star, whereas the big thin spectral lines correspond to a big star. Now, why is this important? Well, if both stars are the same temperature, the small stars can be dimmer and the bright stars can be brighter. Remember the luminosity or the brightness of the star. So the luminosity was sigma A T to the fourth. If the temperature is the same, the constant's obviously the same, so area is how big it is. And so that means that the bigger star is going to be brighter. And we also know that the brightness of the star is related to the absolute magnitude. And so that's important because now, by looking at the width of the spectral lines, you can estimate the absolute magnitude of the star. Now why does that matter? Well, remember, how do we find distance to a star? As Earth goes around the sun, we look at the position of the star, and that position shifts, and we know the distance is 1 divided by parallax. Okay. Well, if the star is really, really far away, then the parallax is so small, it's going to be hard or impossible to measure. So another way of finding distance when we looked at magnitudes was 10 raised to the power apparent magnitude minus absolute magnitude plus 5 divided by 5. So that means you look at the star and that would tell you the apparent magnitude. And then what would happen is if you measure the width of the spectral lines, you could get an estimate of the absolute magnitude. Plug those numbers into this formula, and now you've got a measure of the distance to the star. Well, this is a fantastic tool. In fact, this is so spectacular, they call it sometimes spectroscopic parallax. I don't really think that's a great name because it is spectro, and I guess scopic. It's definitely not parallax, but I didn't name it. Okay, so spectroscopic parallax is what we sometimes call this. Well, interesting story. Walter Botta comes along. Now, Botta is an interesting person. I think he's an interesting person to talk about because Walter Botta was measuring stars in the Andromeda Galaxy. And let me give you a little story about Botta. Botta was a German citizen. He was born and he had a rough birth. Ended up having his leg dislocated. One leg ended up being shorter than the other. And so World War I comes along and he's exempt from military service because his legs are different lengths. And so he always walked with a cane his entire life. And so while everybody else was off at war, he was studying astronomy. And so after the war, he goes on an expedition with a fellow named Schmidt and convinces Schmidt to study about using a corrector plate on a a telescope with a spherical mirror. That gave rise to Schmidt-Cassegrain and Schmidt-Newtonian telescopes. And then Botta, while working in Germany, discovered one of the first asteroids that crosses Earth's orbit. He got a scholarship to go to America and worked at Mount Wilson Observatory, where together with Fritz Zwicky, he looks at these stars that suddenly appeared in the sky, nova we call them, and discovered that some of them are too bright and there were actually stars that were exploding. So he discovered supernovae and explained the physics of that. Then he went back to Germany. Now, this was in the 1930s. And when he went back to Germany, things had changed. Adolf Hitler had been elected a chancellor, and Botta insisted he could not remain in Germany with Adolf Hitler being chancellor. So he came back to the United States. The German persecutions of the Jews started going, and so he sent money back to Germany to some of his Jewish colleagues so they could bribe the border guards to get out of Germany. Now, the problem was in the 1930s, immigration laws were such that these scientists that got out of Germany didn't really have anywhere to go unless someone had a job available for them. So he volunteered to have his salary cut substantially, like almost in half, so that they would have money available to hire some of these German scientists to help them escape, the Jewish scientists to help them escape from Adolf Hitler and the Nazis. And so this is the kind of guy that he was. He actually applied for United States citizenship, but the problem is that the government lost the application, so they were no better at handling paperwork then than they are today. So what happened was that they asked him to reapply, and he said, well, I'm not the one that lost the application. You go find it. And about that time, the Japanese attacked Pearl Harbor. Well, we declared war on Japan. Japan and Germany are in a mutual aid pact. So Germany declares war on us. We declare war on Germany. He's still a German citizen living in California. So they couldn't figure out what to do with him. It was obvious he was not a Nazi. And so, and had no sympathy with the Nazis. And so, but they couldn't just let a German citizen run around. So they interred him for the duration of the war at Mount Wilson Observatory. Well, that overlooks Los Angeles. Interesting thing is that 1941, Japanese bombed Pearl Harbor. Well, January of 1942, the Rose Bowl, normally played in Pasadena, California, but because all our battleships were sunk in Pearl Harbor, they were afraid the Japanese might attack the West Coast. So the entire West Coast was in blackout conditions, actually for most of the war, and the Rose Bowl was actually played in North Carolina in January of 1942. So he's at the observatory. Most of the other scientists are called up to war duty, and so he has the observatory to himself, and Los Angeles is under total blackout conditions. So he uses the opportunity to study the Andromeda Galaxy using new colored film, which showed that the core of the galaxy had stars that were redder than the stars in the outer parts of the galaxy. And there were these two satellite galaxies that go orbit around the Andromeda Galaxy, and they were also a little bit redder. And so he said, well, why are these stars redder? Well, how do you study stars? You do the spectrum of them. So he measured the spectrum of stars in the outer part of the galaxy versus in the middle of the galaxy and the satellite galaxies, and he realized that there were, first of all, there were some interesting differences here. The stars in the outer part of the galaxy had all the different spectral types, O, B, A, F, G, K, and M, but these others had mostly later spectral types, G's, K's, and M's. Well, without the blue light, that's why it looked redder. The bigger difference he discovered was that the stars in the outer parts of the galaxy had all the same spectral lines the sun has, but these other stars tended to have fewer of the things that were not hydrogen and helium. Now, if you remember, things that are not hydrogen and helium we call metal. So he says we got two types of stars, two populations of stars. So he calls them population 1 and population 2. So the population 1 star, this is like the sun. They have some metals in them, all the different kinds of other elements. They are all the different spectral types, and they tend to be all ages of stars. Sun's an example of population 1 star. In fact, actually, most of the population 1 stars are younger than the population 2. The population 2 stars have very few metals. They're usually just the later spectral types, and they're older stars. Now, I will point out that in modern astronomy, we don't really talk that much about stellar populations, because it's not just like you have old and young stars. There's like a continuum of them. But for this class, I think it's kind of a useful as a pedagogical tool to talk about populations of stars, because we find that this helps us understand when you're first learning astronomy kind of how stars are arranged in the galaxy. So the sun is a population 1 star. All the stars in our neighborhood, almost all the stars in our neighborhood are population 1 stars. There's a couple of population 2 stars, and they're not moving the same as the rest of them. Some of the higher proper motion stars are population 2. So that's an interesting thing. And that'll help us understand, well, a little bit more about the structure of the galaxy when we get. So that's the idea that I wanted to get across, with a little bit extra stuff about spectral types.